Hello, my name is Cecilia Valdes, and this is my lab 3 for Physics 2211. This lab is sectioned into two different parts. For the first part, what we want to find is the mass of a black hole from a simulated trajectory using GlowScript. And for the second part, what we want to find is the initial velocity in which a spaceship must travel in order to fly along the hole without getting absorbed by it or without running into it. The preview of our results is that the mass of the black hole was of 6.62 e to the 21 kilograms, and the initial velocity was negative e to the 7,8 e to the 7,0 meters per second. The main models and principles used for this lab are Newton's second law of motion, or the momentum principle, which allows us to break force into parallel and perpendicular components. And we also use the force due to gravity equation quite a bit in position and velocity update formulas, which are all written here. For this part of our lab, our system was considered to be the black hole and our surroundings the star. And for the calculations, we used a gravitational constant of 6.7 e to the negative 11. The mass of the star was considered to be 2 e to the 30 kilograms, and our change in time was considered to be a day, or 86,000 seconds. We also used a seed, which is the string of my email, which gave us a unique set of values for this trajectory. So for the code, we began by calculating the initial and final momentum, given the mass and the initial and final velocity. Then we calculated the change in velocity by calculating the difference between the initial and final velocity. We did kind of the same thing for the change in momentum. We calculated the difference between the initial and final momentum. And we calculated the change in momentum over the change in time, or dPdt, and we renamed this as our Fnet. We then calculated Fnet parallel and Fnet perp by calculating dPdt parallel and perp, which are mathematically equivalent. And finally, we calculated our mass of the black hole by rearranging the force due to gravity formula by taking our mass to be equal to the magnitude of net force times the r squared over the constant of gravity over the other mass. So our results gave out that the mass of our black hole was 6.62 e to the 21 kilograms, and the components were the ones that are below written. For the second part of this lab, our system is the spaceship and our surroundings are the black hole and the planet, and we consider different masses, the one of the planet and the one of the ship, and the gravitational constant to be part of our initial conditions for the code. For this part, we used the equation of force due to gravity a lot, as well as a position update formula and velocity update formula. We began by calculating the r vectors to then use them in the force due to gravity formula for the force on the black hole on the planet, and then for the one of the ship on the planet, and then we calculated the net force by adding these two forces, as you can see. And we did the exact same stuff for the black hole on the ship and for the planet to the ship. And we finally used the velocity and the position update formulas to calculate the velocity of the planet and of the ship, as well as the velocity as the position of the planet and the position of the ship. We used trial and error, and we figured out that the negative x, that the x component of the speed of the ship is a negative 8 e to the 7, and the y component is 8 e to the 7. And that's what it took for the planet, for the ship not to crash into the black hole. Our possible sources of error were mainly that the black hole mass had to be calculated by taking the average of many values, and we don't know how accurate this value is to the real mass. And also the fact that we used trial and error to calculate the velocity might not give us the most accurate answer, as the code was not that strict to the rounding of the numbers. For the what does it mean question, the net force and its parallel and perpendicular components are not the same as the parallel and perpendicular components of dPdt, because although they are mathematically equivalent for this lab, the difference is that the change in momentum can be calculated right away, but we need the mass of the object to calculate the net force. And well, in order to enter the orbit of the black hole, you would need to have a smaller initial velocity that allows it to be more close to the black hole.